Hello. So this is a video about I'm just reviewing what I did in class or self-learning. And it's not like tutorials, so I'm not teaching anything here, but I just want to improve my explanation skills and English skills. And by reviewing what I did today, it sticks on my head better, so I'm doing this. That's the purpose. And today I have reviewed the um previous class the third previous class review and second last class review. So I'm gonna go over them. So first I learned process states. So I'm going to explain all these process and what kind of pattern do they have. So the first pattern. So whenever new process is coming to this new state, and then long-term scheduler pick new process and then place them in ready queue. So things called scheduler and long-term scheduler picks up the task here and then put it on the ready state, ready queue. And from ready queue to run queue, a short-term scheduler pick up the process from here and then put it on, sign it on the run state, run queue. So that's the usual basic uh, process. And after the run state is over, then it goes to terminate state, and that's the end. That was the first pattern of the process. And the second pattern of the process is one something on running state, but there's higher priority task coming to run state, which is called PH. I forgot what PH is. Priority halt. I don't know. Whenever PH comes in this run queue, P1, it's stopped, and when it's stopped, it goes back to ready queue because it's running. PH is running here. And then once pH is stopped, when pH is done, it goes to terminate state, and then the task can come from ready state again, and one is eventually able to go to run state and finish that task too. So that was the second pattern, and there's another pattern that process can go to ready state, which is time quantum. Uh, Time quantum is something. What was time quantum? Right. It's using like a round robin method. So it's like if there's three tasks in ready state, the run state process 5 milliseconds each, and then it goes over each task. So once the first task is done for 5 milliseconds, it go back to ready state and then process the second one and then process only 5 milliseconds and then goes to the second process goes back to ready state and then repeat that process and then eventually the task will be done completely by processing 5 milliseconds each time and then goes to terminate state. So that is time quantum, and that in that case it needs to go back to ready queue. Uh, one process. So there's a third pattern. One process need to access IO task. It goes to block wait and block state. Okay, so whenever there's IO request, whatever process having needs to go back to needs to go to wait or block state. But if there's like wait or blocks, let's say wait or block state has capacity of four process, and IO1, IO2, IO3, and IO4 comes in this block already. And there's one more task. If there's one more task coming to this state, and there's more than more numbers, in that case, there's more numbers coming more than capacity numbers. So it cannot store any more value, any more process here. In that case, it goes to suspend wait. And once what process now? Yeah, so it goes to suspend wait. And if there's more, like if there's more IO request and it fills suspend wait capacity too, then it goes to processing. Then it goes to suspend ready. And once it comes to suspend ready, it doesn't go back like this way, but it actually goes back to ready state once it got space. And this is done by MTS. This this process is done by LTS. This process is done by uh, STS, and this one is done by MTS. So this is the scheduler process. And there are some terminology that I learned. So new is the process is in storage of being created. So new task coming. And ready state is the place where it's or stored. The process needs to be done in CPU. The running state is the CPU working, like doing the process. Waiting is um, the waiting phase where process needs to how to say it works whenever the process is too much and when it requires like IO request and higher priority task comes, then wait block gets those process. And terminate is the process has completed. Yeah, so this is what I learned from this process state. So PCB. Okay, I'll explain what are those. So process ID is like they all have ID. It's just ID. And program counter. I points which process has to be done next. So it's just a pointer. And process state. So it shows whether the process is currently running or stopping. Priority is like giving the number and then deciding the priority. Registers. I heard this is uh, fast shot memory. Probably doesn't have much capacity, but um, it stores the information of execution of instructions and list of open files used for reading or writing operations and I/O devices. It shows which task is stored in I/O devices currently. Okay. All right, so I'm going to explain about context switching. Um, right. So this is explaining when the process requires switching. So first it starts processing from process zero. So it is this time executing, but it needs to stop because process P1 might have like higher priority. And then it's switched to process one execution. And then whenever process one is done, then it goes back to process zero. And there's gap between those execution, like this time and this time. And this is the time of like a waste time because whenever process zero needs to switch to process one, the resource need to be allocated and allocate or for process one. And whenever process one is done, resource needs to be deallocated and another resource is allocated for process zero. So that is what those gap is. So yeah, this switching has some waste, but you can process higher priority process first. Okay, so arrival time. Arrival time is, oh yeah, whenever this is the time when the process arrives at ready state. It's not when a process come out of and then goes to running state. No, this is the time whenever whenever process is arrived on ready state. So exit time. Exit time is this is where terminated state. So whenever it's done, complete. So response time. This is interesting one. Time at which the process gets to CPU for the first time minus arrive time. So when the process arrive running state minus when the process arrives at ready state. So between this time between here and here is the response time. CPU scheduling. Okay. Burst time is the total time of taken by process for its execution on CPU. So yeah, running time, turnaround time. So this is showing the time when the process arrive at ready state until the termination state. Total time of the process. Waiting time. Waiting time is this showing the total time of the process was at waiting state. So it's showing the time. It is showing the time that process needed to be at waiting state. Throughput. It is shown is a way to find efficiency of CPU. Yeah. Okay, CPU scheduling algorithm. So there's two types, preemptive and non-preemptive. And preemptive is the one which can decide priority. So whenever higher priority tasks comes into the system, that's executed first. And non-preemptive doesn't have priority, so it is first come, first serve. So there's four types. First come, first serve, which is non-preemptive, preemptive. Shortest job first, which can be, I guess, preemptive. Round robin is there's no priority, but it's doing like every task, so it's non-preemptive, I guess. And priority scheduling must be preemptive. So this is what I learned from operating system class, and there's one more class that I did this week, so I need to review them too.